Hello and welcome to this video that is about masses of atoms. We're going to look at the masses of subatomic particles, the masses of atoms, isotopes of elements, and weighted averages of naturally occurring isotopes. So far we have looked at these three main subatomic particles, protons, neutrons, and electrons, and we've seen what their electric charges are. What about their masses? We define a proton as being roughly 1 AMU. That stands for atomic mass unit. And the unit was created to correspond to the mass of a proton, which is, in grams, 1.67 times 10 to the negative 24th grams. That means we'd have a 0 point and then 23 zeros and then 167 grams. That's tiny, and it's a lot of zeros. And in order to simplify that, the atomic mass unit was set up to help us quantify that in a simple way. Interestingly, a neutron is the same mass as a proton, 1 atomic mass unit. And an electron is so tiny, we generally ignore the mass. In fact, a proton or a neutron would be about 10,000 times larger than an electron. So when we look at mass of atoms, we consider the mass of the electron to be negligible. So we have talked about the symbol of each element being unique, and each element has a name. Let's look at some of the numbers that are represented on the periodic table. And a really important one is the atomic number. The atomic number right here is this number. For lithium, it's a number 3. What is it? It's the number of protons that lithium has. Each lithium atom has 3 protons. It identifies the type of atom. If 4 protons were present, it wouldn't be lithium. It would be beryllium. If 5 protons were present in this atom, it would not be lithium or beryllium, it would be boron. The number of protons identifies that type of atom. Another important number is the atomic mass. That would be this number down here. The atomic mass is actually the average mass of an atom of that element. It is primarily due to the protons and neutrons, because remember, that's where the bulk of the mass is. It's measured in AMU, or atomic mass units. Another term for the atomic mass would be the mass number. The mass number is the number of protons plus the number of neutrons. We can round this number up to an even 7. Knowing that, how many neutrons are in the nucleus? Pause the video and think about that for just a minute. In the nucleus of one lithium atom, how many neutrons exist? Well, if the mass number is 7, and the mass number equals the number of protons, which is 3, plus the number of neutrons, how many neutrons are there? Well, there would be 4. 7 minus 3 equals 4. Lithium has 4 neutrons. Remember, atoms of the same element always have the same atomic number. Do atoms of the same element always have the same atomic mass? No, that is why we get that funny big number that we kind of round to the nearest whole number. But atoms of the same element do not always have the same atomic mass. What accounts for this? Well, atoms of the same kind of element must have the same number of protons, but they do not have to have the same number of neutrons. We call atoms of the same element that have different numbers of neutrons isotopes. Here is an example of hydrogen isotopes. Hydrogen can have just 1 proton with no neutrons. We could have a hydrogen atom that has 1 proton and 1 neutron. It's called deuterium. Or a hydrogen atom with 1 proton and 2 neutrons, called tritium. Obviously, the mass would be different for each of these. this would have a mass of 1 atomic mass unit, 2 atomic mass units, 3 atomic mass units. But notice that for every hydrogen atom, it only has 1 proton. That is its identity. These are 3 different isotopes of hydrogen. Here are some isotopes of carbon. Here is carbon 12 because it has 6 protons and 6 neutrons. So its atomic mass would be 6 for the 6 protons plus 6 for the 6 neutrons. That gives us atomic mass of 12. Here, an isotope of carbon as carbon 13 because it has 7 neutrons instead of 6. So its atomic mass is 6 for the number of protons, which of course stays the same for every carbon atom, plus 7 for the atomic mass of the neutrons. That's 13 atomic mass units. We call that carbon 13. Carbon 14 has 8 neutrons. 6 plus 8 gives us a mass of 14 atomic mass units. And so how do scientists account for and represent the different atomic masses of isotopes? Let's explore that question by looking at an example. Let's look at the isotopes of boron. There is boron 10 and boron 11. Boron 10 has a nucleus with 5 protons and 5 neutrons. Boron 11 has a nucleus with 5 protons and 6 neutrons. So scientists look at the naturally occurring abundance of these different isotopes. And when they look at how much out of all the different boron atoms that exist naturally, about 80% of all those boron atoms are the boron 11 isotope. About 20% of them are the boron 10 isotope. And we calculate a weighted average in this way. 4 out of 5 boron atoms are boron 11. So we multiply 4/5 by 11 atomic mass units. Then we're going to add the weighted fraction for boron 10. 1 out of 5 of the naturally occurring number of boron atoms is boron 10. So 1/5 times 10 atomic mass units. And when we multiply 4/5 times 11 atomic mass units and we add the product of 1/5 times 10 atomic mass units together, we get this weighted average to be 10.8 atomic mass units. And that is the number that's represented on the periodic table. The average atomic mass of an element is the weighted average mass of all the naturally occurring isotopes of an element measured in atomic mass units according to their natural abundances. Some advanced ideas: find other examples of isotopes. Can you calculate the number of neutrons in each of those isotopes? How are radioactive isotopes used to tell time? Other ideas that you might have or questions. I look forward to seeing what you come up with, and we'll see you in class.